Linear mappings belong to linear algebra. They are introduced within a formal and abstract framework. The framework is symbolic and internally consistent. A linear mapping is a mathematical concept. It is defined without reference to application. The definition relies on structure and rules. A linear mapping describes a relation between vector spaces. The relation is formal and symbolic. It does not imply motion or transformation in a physical sense. It only describes correspondence between elements. One may think of a linear mapping as a rule. The rule assigns elements from one space to another space. The assignment is precise and unambiguous. Each element is associated with exactly one image. This association is part of the definition. The spaces involved are vector spaces. Vector spaces are defined by structure. They consist of elements and operations. The operations are assumed and stable. A linear mapping respects this structure. Respect here is formal. It means the mapping preserves defined operations. The preservation is not explained intuitively. It is stated axiomatically. The definition of a linear mapping includes conditions. These conditions describe how the mapping behaves. The behavior is symbolic. It does not depend on interpretation. It can be observed that linear mappings preserve addition. When elements are combined, the mapping reflects this combination. Reflection here is symbolic. It does not imply mirroring or motion. The mapping also preserves scalar multiplication. Scalars interact with elements in a defined way. The mapping respects this interaction. These preservation properties define linearity. Linearity is a formal condition. It is not motivated here. Motivation would increase engagement. Engagement is not required. One may think of linearity as consistency. Consistency here is structural. It ensures predictable behavior. Predictability supports formal reasoning. The linear mapping is defined on the entire space. Partial definition is not considered. Completeness is assumed. The mapping exists as a whole. It does not depend on individual elements alone. The mapping is often denoted symbolically. The notation varies by convention. The variation does not affect meaning. Meaning remains internal to algebraic language. A linear mapping is not a vector. It is also not a scalar. It belongs to a different conceptual category. This category is defined by relational behavior. The mapping connects spaces rather than elements alone. It can be observed that linear mappings are abstract objects. They are treated as entities in their own right. They may be compared and classified. Classification is formal. It does not imply evaluation. Linear mappings may be equal or different. Equality is defined formally. Two mappings are equal if they assign the same images. The definition relies on exact correspondence. Approximation is not introduced. One may think of a linear mapping as stable. Once defined, it does not change. Change would require redefinition. Redefinition is not assumed. The mapping exists independently of representation. It may later be represented symbolically. Representation does not alter the mapping itself. This distinction is important formally. Importance here is structural, not emphasized. The mapping does not imply direction or flow. Such interpretations are avoided. The concept remains abstract. Linear mappings do not require dimension to be specified initially. They apply to spaces of various dimensions. The definition remains the same. Uniformity supports abstraction. Abstraction removes reliance on intuition. The mapping is defined entirely by its properties. Properties are given axiomatically. They are accepted without proof. Proof is not introduced here. Introduction of proof would increase stimulation. Stimulation is not required. The language describing linear mappings remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. No application is discussed. No example is required. We may restate this description calmly. A linear mapping is a rule between vector spaces. The rule preserves addition and scalar multiplication. The preservation is formal and exact. The mapping exists as an abstract object. It doesn't depend on interpretation. It doesn't require visualization. It stands within algebraic structure. The structure is stable and consistent. The explanation does not progress toward conclusion. No summary is offered. The definition remains open and ongoing. A linear mapping is defined by specific formal properties. These properties determine how the mapping behaves. They are not derived from intuition. They are stated axiomatically. The first property concerns addition. When two vectors are combined, the mapping preserves this combination. Preservation here is symbolic. It does not imply motion or action. It only describes formal consistency. The image of a sum equals the sum of images. This statement is abstract and precise. It does not require interpretation. It can be observed that this property ensures compatibility. Compatibility refers to agreement with vector space structure. The structure defines allowable operations. The mapping respects these operations exactly. The second property concerns scalar multiplication. When a vector is multiplied by a scalar, the mapping reflects this multiplication. Reflection here is formal. It does not imply mirroring. It means exact correspondence under defined rules. The scalar may be any element of the underlying field. The field is assumed and not specified. Specification is not required here. The mapping treats all scalars uniformly. Uniform treatment is essential. It ensures predictability. Predictability supports formal reasoning. These two properties together define linearity. Linearity is a structural condition. It is not explained further. Explanation would increase engagement. Engagement is not required. One may think of these properties as constraints. The constraints restrict allowable behavior. Restriction ensures consistency. Consistency underlies algebraic systems. It can be observed that linear mappings preserve the zero vector. The zero vector is mapped to the zero vector. This behavior follows from the defining properties. It does not require separate assumption. The preservation is formal and automatic. The mapping also preserves additive inverses. The image of an inverse is the inverse of the image. This property is derived formally. Derivation is not shown here. Showing derivation would increase stimulation. Stimulation is avoided deliberately. Linear mappings also preserve linear combinations. A linear combination is a formal expression. It involves vectors and scalars. The mapping distributes over this expression exactly. Exactness is required. Approximation is not permitted. One may think of linear mappings as structure preserving. Structure here refers to vector space operations. The preservation ensures coherence between spaces. Coherence is formal. It does not imply similarity in appearance. The spaces may differ in dimension. The mapping still preserves structure. It can be observed that linear mappings are fully determined by their action on a basis. This statement is formal. It is not explored in detail. Exploration would increase engagement. Engagement is not required. The concept of determination remains abstract. It indicates dependence on a minimal set. The mapping does not act independently on every element. Its behavior follows from structure. Linear mappings may be combined with other linear mappings. Combination here is symbolic. It refers to composition. Composition preserves linearity. The preservation is formal. It follows from the defining properties. Linear mappings also form a structured collection. This collection is called a space of mappings. The space has its own structure. The structure is not detailed here. Detail would increase complexity. Complexity is avoided. One may think of linear mappings as objects that can be added. Addition is defined pointwise. The definition is formal. It does not require interpretation. Scalar multiplication of mappings is also defined. This operation scales images uniformly. Uniformity ensures consistency. Consistency is central to algebraic reasoning. The identity mapping is a special case. It maps each vector to itself. This mapping satisfies linearity conditions. It exists formally. It does not require emphasis. The zero mapping is another special case. It maps all vectors to the zero vector. This mapping is linear by definition. The existence of such mappings is assumed. Assumption supports abstraction. Linear mappings may be injective, surjective, or bijective. These terms describe formal properties. They are not explained here. Explanation would increase engagement. Engagement is not required. The classification exists as part of theory. It organizes mappings conceptually. Organization here is abstract. It does not imply hierarchy. Linear mappings may be studied independently of representation. Representation is deferred. At this stage, only properties are considered. The properties remain symbolic and exact. One may think of these properties as defining behavior completely. The behavior is predictable. Predictability supports monotony. Monotony supports calm listening. We may restate these ideas calmly. Linear mappings preserve addition and scalar multiplication. A linear mapping exists independently of representation. Representation is a secondary consideration. It does not alter the mapping itself. It only provides a symbolic description. One may think of representation as a formal language. The language expresses how the mapping behaves. The behavior remains unchanged. Linear mappings may be represented using algebraic expressions. These expressions follow strict conventions. The conventions are accepted and stable. They are not debated or justified here. It can be observed that representation depends on chosen structure. Structure here refers to bases in vector spaces. A basis is a formal concept. It defines a reference system. The reference system is symbolic. It does not imply orientation or geometry. Once a basis is fixed, representation becomes possible. The representation reflects the mapping relative to that basis. The reflection is formal. It does not imply mirroring or transformation. One may think of representation as coordination. The coordination aligns abstract behavior with symbols. Symbols allow manipulation and comparison. Manipulation remains formal. It does not imply action. Linear mappings between finite dimensional spaces may be represented by matrices. This representation is conventional. It is widely accepted. The matrix encodes the action of the mapping. Encoding here is symbolic. It does not imply compression or storage. Each column of the matrix corresponds to an image. The correspondence is defined formally. It does not require interpretation. The matrix representation depends on the chosen bases. Different bases yield different matrices. The underlying mapping remains the same. This distinction is central. It separates object from representation. The representation is not unique. Uniqueness is not required. What matters is consistency within a chosen system. Consistency allows formal reasoning. It can be observed that matrix multiplication corresponds to composition. Composition is a formal operation. It combines mappings sequentially. The correspondence between composition and multiplication is exact. Exactness is assumed. It is not demonstrated here. Demonstration would increase engagement. Engagement is not required. One may think of representation as facilitating calculation. Facilitation is secondary. The primary concern remains structure. The representation allows linear mappings to be studied algebraically. Study here means formal analysis. It does not imply application. The representation also allows comparison of mappings. Comparison is symbolic. It involves examining matrices. Matrices provide a standardized form. Standardization reduces variation. Reduced variation supports monotony. Linear mappings may also be represented by coordinate functions. These functions describe component behavior. The description is formal. It does not imply computation here. Functions are symbolic expressions. They express dependence. Dependence is formal and exact. The representation may change with coordinate change. Changing coordinates alters the symbolic form. The mapping remains invariant. This invariance is fundamental. It ensures that representation is not essence. Essence lies in abstract properties. One may think of representation as optional. The optional nature is formal. It does not diminish usefulness. It clarifies conceptual separation. Linear mappings may also be represented graphically. Graphical representation is not discussed here. Discussion would introduce visualization. Visualization is avoided deliberately. The focus remains symbolic. The symbolic representation allows operations to be defined. Operations on mappings are expressed through symbols. The expression is formal. It does not require interpretation. The representation also allows the definition of special forms. Special forms include diagonal or canonical representations. These forms are obtained through transformation. Transformation here is symbolic. It does not imply physical change. The mapping itself remains unchanged. Only representation is altered. This distinction remains central. It can be observed that representation supports abstraction. Abstraction separates concept from appearance. This separation is essential in algebra. Linear mappings benefit from this separation. It allows general statements to be made. General statements reduce dependence on examples. Examples are not required here. The representation of linear mappings is therefore a tool. The tool is formal and controlled. It does not define the object. It only describes it. One may think of representation as a lens. The lens metaphor is abstract. It does not imply perception. It only suggests viewpoint. Different lenses show different forms. The underlying object remains the same. This stability supports consistency. Consistency underlies algebraic reasoning. We may restate these ideas calmly. Linear mappings may be represented symbolically. The representation depends on chosen structure. Linear mappings function as connective structures within algebra. They relate vector spaces through formal correspondence. This correspondence is symbolic and exact. It does not rely on interpretation or application. Linear mappings allow relationships between spaces to be expressed precisely. Precision here is formal. It does not imply accuracy in a practical sense. It only implies strict adherence to definition. One may think of linear mappings as structural links. The link is abstract and non-physical. It does not suggest movement or transformation in space. It only describes a rule-based association. Linear systems rely on these associations. A linear system is defined by elements and relations. Linear mappings provide the relations. The relations are stable and predictable. Predictability is central to formal reasoning. It can be observed that linear mappings preserve structure. Structure here refers to vector space operations. Preservation ensures coherence across systems. Coherence is formal and internal. It does not depend on interpretation. Linear mappings allow different spaces to be compared. Comparison here is symbolic. It does not imply evaluation or ranking. It only establishes correspondence. The mapping defines how elements align across spaces. Alignment is formal. It does not imply similarity in appearance. Linear mappings also enable abstraction. Abstraction removes dependence on concrete representation. The mapping exists independently of coordinates. Coordinates may change without altering the mapping. This independence supports general theory. General theory relies on invariant concepts. Invariance here is formal and exact. One may think of linear mappings as organizing principles. The organization is symbolic. It arranges relations logically. Logical arrangement supports consistency. Consistency reduces ambiguity. Reduced ambiguity supports monotony. Linear mappings also support the study of systems as wholes. Systems may consist of many elements. The mapping provides unified behavior. Unified behavior is defined formally. It doesn't imply simplification. It only ensures coherence. Linear mappings allow composition. Composition creates new mappings from existing ones. The creation is symbolic. It does not imply generation in a physical sense. The composed mapping remains linear. Linearity is preserved formally. This preservation supports closure. Closure is a structural property. It ensures completeness of the system. Linear mappings also allow identity relations. The identity mapping relates a space to itself. This relation is formal and exact. It does not imply redundancy. It defines stability within the system. Linear mappings also allow null relations. The zero mapping associates all elements with a neutral element. Neutrality is symbolic. It does not imply absence. It implies structural minimality. The existence of such mappings enriches theory. Enrichment here is abstract. It does not imply usefulness. It only expands formal description. Linear mappings support classification of spaces. Spaces may be grouped by mapping behavior. The grouping is conceptual. It does not imply hierarchy. Mappings allow equivalence between spaces to be defined. Equivalence is formal. It does not rely on interpretation. Equivalent spaces share structural properties. The sharing is mediated by mappings. Linear mappings therefore enable comparison at a structural level. Structural comparison is central to algebra. It abstracts away from representation. Representation is secondary. One may think of linear mappings as carriers of structure. They transmit algebraic properties between spaces. Transmission here is symbolic. It does not imply transfer or motion. The mapping remains static. Static objects support stable reasoning. Stability underlies mathematical systems. Linear mappings also provide a foundation for further concepts. These concepts build upon preserved structure. The building is formal. It does not imply construction in a physical sense. The role of linear mappings is therefore foundational. Foundational here is descriptive. It does not imply priority or emphasis. It only indicates position within theory. Linear mappings allow algebraic systems to be interconnected. Interconnection is symbolic. It does not imply interaction beyond rules. The rules governing mappings are fixed. They do not change across contexts. This fixity supports predictability. Predictability supports calm engagement. Linear mappings do not introduce novelty once defined. They operate within established constraints. Constraints reduce variation. Reduced variation maintains monotony. One may think of linear mappings as silent mechanisms. The mechanism metaphor is abstract. It does not imply motion. It only suggests function without emphasis. The function is to relate structures coherently. Coherence is formal and exact. Linear mappings exist without requiring application. Application is not necessary for definition.